So today's lesson is about how we go about stating interaction results. So we've designed a multi-way analysis of some factors, two or more factors, and we have a two-way analysis of variance, let's say, for example, and we get a significant statistical interaction between our two factors. So in our ANOVA table, the factor 1 cross factor 2 interaction is statistically significant. So how do we go about stating those results in a results section of a paper that we might write as biologists? So I think it helps to have an example. So let's create a problem here where we are looking at this question. Does the sleep aid, we imagine a drug that some drug company has come up with, does the sleep aid, we can give it a name, let's call it Sandman. It's a nice name for a sleep aid. Does the sleep aid Sandman affect men and women and you know, we can kind of assume that they all are from some matched population in some way differently. So we're curious about the different response of men and women to Sandman. Now, let's think about this question. What would the experimental design actually be? So what we need to do is identify our independent and our dependent variables. So what would our independent variables be? Obviously, we're asking about men versus women, so one of them is sex. And the levels within sex are male, female. Okay, so that's one independent variable. What's the other one? Well, we're asking about the sleep aid Sandman, so that must be the other variable, drug. And presumably, if we were being smart about this and complying with the FDA regulations and so forth, we would have to have some kind of a placebo that we administered to some part of the population as well as Sandman. So our two levels would be placebo and Sandman. Okay, so we can understand our independent variables as a two-way design with sex, male and female, and drug, placebo, and Sandman as our two levels of drug. Okay, so we would have four possible treatments. What about our dependent variable? Actually, when we stated the question, we didn't really put one down, so we really should. How would we measure the effect of Sandman? Probably sleep period, you know, something like that. We might have some baseline sleep period and look at change in the length of someone's sleep obtained through a night. There are a lot of ways we could do this. We could put activity things on their bodies and measure how much time they're actually asleep out of a period of time from when they go to the bed and so forth. So there are lots of ways we could do that, but let's just simplify and call it sleep period. Okay, so we have our dependent variable, our independent variables, and if we think about our question, does the sleep aid Sandman, does going from placebo to Sandman differ as a function of sex? In other words, if we were to fill in numbers here, can we just say that, you know, we're going from 6 to say 8 hours of sleep with Sandman? Do we have a different number in terms of that transition? Is it just the same plus 2, or maybe it doesn't affect women as much, or vice versa? You know, doesn't matter, but that would be a differential effect of the drug depending upon sex, right? And we would be measuring it by our interaction. So let's just remind you how to set up this in JUMP if you are setting up the effects in the model. And by the way, we would obviously use fit model for this, not fit y by x, because fit model is our more general one where we can actually put in more complex situations. x fit y by x is for one-way designs. So we have sex, we have drug treatment, placebo versus drug, and we have sex cross drug treatment. So there are three effects in our model. The main effect of sex, is there a sex difference? The main effect of drug, is there a drug difference? And does the effect of drug depend upon sex? By the way, just as a matter of course, if we design a two-way factorial experiment, typically we will be interested in this bottom line. In fact, I sometimes call this the Blibble principle. The bottom line is the bottom line. We should be interested, so this should be the effect of interest. Usually, if we have two factors, we should be designing this two-way factorial experiment in this complex a manner, in other words, with two factors, because we are interested in that interactive effect. If we're not interested in it, maybe we should design a simpler experiment. Okay, we may come back to that at a later point. So, let's say we get some results. So how do we state these results? First of all, just in terms of an ANOVA table. I showed you an ANOVA table for a one-way analysis of variance, and we have all the same headings. If we're going to write a complete table, we have a source of variation, we have degrees of freedom, we have sums of squares, we have mean squares, we have F, and we have probability of a greater F, in other words, P, which we all obtain from SAS Jump. Our fit model output will give us all of these things, and I'll show you in class where to exactly find them. So we have our effects in the model: sex, drug treatment, sex cross-drug treatment that we've set up, and this will come out, and error. By the way, this is usually obtained from the whole model analysis, and we just write that line in here. We'll get obviously degrees of freedom, so we have what, two sexes, so we have 1 degree of freedom, we have 2 drug treatments, 1 degree of freedom, and we have sex cross drug, so it's going to be A minus 1 times B minus 1 if this is our A and this is our B factor. So we have 2 minus 1 times 2 minus 1, or 1 times 1, and we have 1 degree of freedom. And depending upon our sample size, we would have whatever for our error. So let's imagine that we get some F values here, so I'm just making up these values. 1.36, 6.10, and 4.22. Okay. And we get a p-value associated with each of those. And again, I haven't looked these up, so I don't know if they're realistic to go with these particular F's. And of course, it would depend upon degrees of freedom and all that good stuff. But let's imagine we get this situation where, and of course we don't have an F and a P associated with the error, right? Because there's no error to test it over. All right, so you understand this, and we are really paying attention to our statistically significant p-value associated with the interaction term. The real question I want to get to today, so this is how we would present it, and obviously we would fill in these numbers here from Jump. What I really want to get to today is how we would make our first statement about this interaction, because this p-value, p is less than alpha. If we set alpha equals 0.05, right, which is fairly typical, we are finding a statistically significant interaction between sex and drug. So in fact, we could write there was a statistically significant interaction between sex and drug. F equals, P equals, in parentheses. So I've taught you already, we don't put the F and the P value in our sentence. And I've taught you some things, some principles that I hope would make you not want to write it this way, actually. So there was a statistically significant interaction between sex and drug. Why wouldn't I suggest writing it that way? Is it wrong? Not really. Is it informative? No. It's not very informative biologically to say there was an interaction between sex and drug. What does that mean? The problem is that interaction has a statistical meaning and it has a biological meaning. So are you saying that drug somehow interacted with sex? Because it sounds like that when you put it that way. So you really need to rephrase it. The drug is not interacting with the sex of the individual. It's not changing someone from male to female or something, or the male-female is not altering the drug. So because the word interaction, I almost wish there was a different word we would use when we were talking about statistical interaction. And there are other ways you can say. You can say non-additive. So let's try that. Let's say the effect of sex and drug was non-additive. F equals and P equals. Does that help? It's kind of nondescript. Again, it's not really incorrect statistically, because an interaction does mean that it's non-additive, but it's not very helpful, again, to someone trying to figure out what you mean. I mean, what is meant by additivity? You're kind of forcing the reader of your statement to figure out what additivity would be. How do you add the effects of sexes? And notice that both of these statements have nothing about the y variable in them. Where's the y variable even mentioned in either of these? It's not. There's no mention of sleep period. So let's try to make this a little bit better. Let's see. How about this? The effect of Sandman. Well, this is better because we're talking about the effect of the specific drug. The effect of Sandman on sleep. Hey, we've mentioned our y variable now. Effect of Sandman on sleep depended on sex. Ooh, I'm liking this better. And then we could say F equals and P equals, right? So there was a dependency of the effect of Sandman, going from left to right in our table, remember, on the sex of the individual. I kind of like that. But I think we can do even better. How about the effect of Sandman on sleep differed for males and females? I mean, there's a straightforward declarative statement, and our evidence is F equals P equals, so just like above. So this is really nice. We have our y variable here. We have one of our x variables, which we're really interested in, this drug effect, and we're having that drug affecting sleep, but we're asking if that differed for males and females, and the answer is the effect differed for males and females. So we're providing a direct answer to our question. So I think when you're stating results, you want to go back to your question. What was it? Does the effect of Sandman differ for males and females? And here we see, aha, the effect of Sandman on sleep did differ for males and females. Here's our evidence. And we would, of course, provide some kind of a graph to show how big that difference was and so forth. But I think this is the most effective and simplest way to state a two-way interaction where we are asking about a differential response of two groups. So if we have males and females, if we have genotype, if we have species, when one of the factors is not really something we're manipulating, we might be controlling in terms of the number of males and females we have, but we're not kind of controlling that sex. We're not like changing the genotype, although we could mutate, I suppose, with some species and so forth. We're not making species 1 and species 2. We have two groups that we're comparing the response to something of. Then it really makes sense to state it like this. Now, I want to contrast that a little bit with a different kind of experiment. So, for example, let's imagine that our y variable was something like gene expression. Okay. And we have our independent variables as environmental factors, such as, for example, x1 might be temperature, and because we know temperature affects gene expression, and at the same time, we are looking at nutrient level. So let's imagine we have 3 temperatures, 3 growth temperatures, 10 degrees C, 15 degrees C, 20 degrees C, and we have low, medium, and high nutrient levels. Okay, so we have what? What kind of a factorial experiment is this? This is a 3 by 3 factorial. In other words, it's a two-way design with 3 levels of each factor. And let's say, for example, we get a significant temperature by nutrient level interaction. So we do our ANOVA and we get F equals, I don't know, 8.61 and P equals 0.0013. All right, so we get a significant temperature cross nutrient interaction. Here, these different factors are in a sense equivalent. So we wouldn't necessarily have a bias towards stating the interactive effect in one way or the other. We might say, for example, the effect of temperature on gene expression depended on nutrient level. F equals and P equals. Okay, give our evidence. But we could probably just as easily say the effect of nutrients or nutrient level, either one, the effect of nutrients on gene expression depended on, I like it simple, depended on temperature. We could say growth temperature if we wanted to be specific. Okay? Now, what would favor one way of saying that over another? There might be a reason to do that. For example, if you found first that temperature affected gene expression, and then your second experiment was you added nutrient level variation as well to test whether the temperature effect depended upon nutrient level. If you had that background, you might state it the first way. The effect of temperature on gene expression, which you already knew about, depended upon the nutrient level. So you added a nutrient second, or vice versa for the second one. Now, so you might look at these and say, well, depending upon how I stated it, kind of changes the emphasis a little bit, doesn't it? It truly does, and either way of stating it is absolutely correct. There's not one of these ways that's wrong, but one of them draws attention to one factor, the effect of temperature on gene expression, draws attention to the effect of temperature and the modulating effect of nutrients, whereas stating it this way kind of reverses that. It says the effects of nutrients on gene expression depends upon the modulating effect of temperature. So if you don't have a particular one you want to emphasize, you could say something like the effect of nutrients and temperature on gene expression were non-additive. And that wouldn't be necessarily bad as long as you went ahead and described the nature of the non-additivity. So I'm not going to go ahead and talk about that second level of statements where you describe the nature of the difference in response. We'll get to that when I talk about graphing and showing interaction with graphics, because that's where you really need the help of a visual so that you can describe what's going on. And we'll talk about statements of that kind of thing when we get to that. But right now I just want to leave it as the general statement of an interactive effect. How do you do that? There are two kinds. There's one kind where there's an obvious main group or that you want to use to compare, for example, males, females, species, genotypes tend to fall in that kind of category. Males and females responded differentially. Species A, B, and C responded differentially to some other factor. But when you don't have that, when you have more co-equal kinds of factors or factors that you are varying both of those with your experimental controls, you can state them either way, and I think generally choosing one is best, but you can also state that their effects were non-additive or interactive. The problem there is you want to be really careful that you're not stating it in such a way that it suggests the two things are interacting with each other. Okay, it's not temperature that's interacting with nutrients here. It's the effect of temperature on gene expression that depends upon something else. And that's where statement of interaction tends to go haywire. Is if you state it the wrong way, it can suggest that nutrients are affecting temperature and temperature is affecting nutrients, and that's not what needs to be happening. And in fact, the two-way ANOVA assumes that these are independent variables, that you can manipulate them independently. And one of the biggest flaws of two-way designs is that the two factors aren't manipulated independently, and then interpretation becomes very difficult. So we have to assume that these are independent variables and that when I vary temperature, it's not affecting nutrients and vice versa, that I can control those levels, and at each temperature, the nutrient differences will be maintained. All right. Otherwise, interpretation becomes really, really difficult with two-way designs, and imagine what happens with three-way, four-way, etc. All right. We'll leave it there for now.